Okay. Okay, so last week we talked about the different optimizers and learning rate schedule, right? And so we are almost done with this chapter. Okay, there are still two topics. Okay. The first one is a bigger one. The second one is not so big. Okay, the first one is the dropout. Okay, dropout. Okay, yeah, just like the last week we also talked about the L1, L2, right? I mean, so dropout is also like one technique that we use to fight with the overfitting, okay? Or, you know, this concept is a very interesting concept, okay? It was proposed like in 2012, okay, by Nitish, okay? The idea is kind of interesting, okay? When you apply the dropout, even the state-of-the-art neural network got a 1 to 2% accuracy boost, okay? So not only, you know, you help to fight with overfitting, at the same time, you will improve the accuracy of your model, okay? So of course, like you know, you may feel like this 2% is like not that much, but consider if your model is like already like you know, maybe like 90% like accuracy, then getting 2% accuracy increase is a big thing. Okay, it means like a reduction of the error from 5% to 3%. That's a 40% drop of the error rate. Okay, so that's a big thing. Okay, you shouldn't consider this 2% as a small one. Okay, so okay, so what is dropout? Okay, it's okay, the idea is like this: at every training iteration, okay, every neuron, okay, including the input neurons, okay, but not including the neurons in the output layer, okay, basically like except the neurons in the output layer, every neuron, okay, except neuron in the output layer, participate, you know, just try to throw a dice, okay, throw a dice, and decide this neuron wants to participate in this training iteration or not. Okay, basically we set up a probability P. We call that dropout rate. Okay, so if this neuron throw a dice and it happens that the result, you know, this you know, the outcome is like you know, is lower than this probability P. For example, like say the probability P is 50%, and you throw a dice. Okay, say the dice has like the point from 1 to 10. So as long as you are lower than 5, that means you have 50% chance to get that you know, lower than 5 like points, right? So in that case, okay, this neuron will not participate in this iteration. Okay, but this is done every iteration. So even if this neuron may not participate in this training iteration, in the next iteration, this neuron may, you know, participate again. So this is, you know, kind of interesting approach, because, you know, every neuron gets the chance to take a rest, pretty much. Okay, so the dropout rate, you may ask, like how much is the dropout rate? Usually, it's typically like in between 10% to 50%. Okay, if it's recurrent neural networks, it's around 20 to 30%. If it's like CNN, then it's between 40 to 50%. Okay, we are going to talk about like a CNN and RNN shortly. Okay, right after we finish this chapter. Okay, so after training, okay, so this is done every iteration during training. Okay, so after the training, okay, when you are using this network for inference, okay, then the neurons don't get dropped. Okay, all the neurons will participate in the inference. Okay, that's it. So of course there are a little bit technical detail that we need to take care. Okay, but we are going to get to that shortly. Okay, but basically the basic idea is just like this. Okay, so this is like just an illustration of one iteration. You can see in this iteration, okay, this neuron does not participate. This neuron, okay, so we have, approximately half of the neurons not participating in this training iteration. If you ask me, I will tell you, okay, this dropout rate is maybe said to be like 50%, okay, 0.5. Okay, so when a neuron stop, participating in this iteration, of course, all the associated connections are not activated either. Okay, so this is something you need to know. Okay, so why do I tell you this is an interesting idea? Okay. Consider a neural network as a company. Okay, if you consider the neural network as a company and each neuron as an employee in this company, then can you imagine like if you work for a company, every morning when you wake up, okay, you throw a dice to decide whether or not you want to go to work. Okay, and if the outcome is not good, so you just I will just stay bed and take a rest for the day. Okay, and if the outcome is unfortunately like the otherwise, you go to work for that day. Okay, you do this every day, and eventually the company perform better. That's interesting, right? I mean, if you try to think of it like that, then you will feel like how can it be possible? How can a company or a neural network, whatever you say it, okay, be perform better, okay, when you train it like that? Okay, because if you try to use the company as an example, okay, then at least you will observe the following three very important result. The first one, okay, if a company, okay, has a policy like that, okay, and then assuming that company still survive, okay, assuming that company still survive, of course, like if company doesn't survive, that's unfortunate, right? But if a company survive, okay, then we can probably tell that first the company could not rely on any single person to fill in the coffee machine or perform any critical task. Why? Because if that guy is not coming to to work, then the company will fail to do some very important task today, right? Okay, so basically, like a company has to not rely on any particular person, the company has to, spread, okay, the expertise across several people. Okay, everybody can do, certain job. Okay, say like, if originally you are working for a company to fill in the coffee machine, then everybody has to be able to do that. I mean, because who knows if you are coming to work or not today, right? Okay, same thing. Okay, the second fact we can probably observe is that employees would have to learn to collaborate with many of their co-workers, not just a handful of them. Because I don't know if you know, but the company normally has a hierarchy, right? For example, you are the supporter for some employees. Your job, okay, maybe the outcome of your job may be used by some other people, right, in the company. And also, you may depend on some other people's output to you, okay, in a company. This is very common, okay, which is normally in a company called organization chart, okay, ORG chart, okay, in Western culture. This thing is very important, okay. A lot of jokes, okay, are made, okay, for this ORG chart, okay. But anyway, okay, but at least you understand, okay, if you work for a company, especially for a big company, okay, you have a hierarchy and you are somewhere in the hierarchy. So some people depend on you, and you also depend on some other people, right? But now, because everybody can take a day off from the job, so what do? Everybody, employee will have to learn to collaborate with many of their co-workers, not just a handful of them. Okay, if this guy doesn't come to work, you have to collaborate with other people, not just that guy. You cannot just wait for him, okay, for the input. Okay, you have to be able to collaborate better in the company, okay, in order to survive. Otherwise, you cannot do anything. Okay, if you consider, I have to get something from this particular important person, then if that person take the day off, well, you are pretty much useless, right? Okay, so you have to be able to collaborate better. And the third fact you can observe is that the company will become much more resilient. Okay, if one person quit, it wouldn't make much of the difference, right? Okay, if a company, regularly have say 50% of the employee not coming to work, then say if the company decide to lay off some people, this perhaps is not good for the employee, but you get the idea. It doesn't hurt the company at all, right? Because company can survive, every day, without half of the employee anyway, right? So when the company try to lay off some employee, that's fine. So the company is much more resilient, much stronger, okay? So of course you can replace the company here by the neural networks, okay? So of course, okay, when we compare this thing to a company, okay, after all, this is still strange because, it's unclear whether this idea actually works for companies. Why? Because no company do that, right? No company do that, unfortunately, okay, okay, if we have such a company, I believe everybody wants to work for that company, right? Okay, but it certainly does for neural network, okay? This dropout, turns out to be a very powerful technique, okay? Neurons trained with dropout cannot adapt with their neighboring neurons. They have to be as useful as possible on their own. This sentence basically is exactly the reflection from the first observation of the company example. Okay, also, okay, they must pay attention to each of their input neurons. Okay, this sentence, again, okay, reflect the second fact, okay, from the company example. Okay, the employee has to be able to collaborate better. Okay, and the neurons end up being less sensitive to slight changes in the input. So in the end, you get a more robust network that generalizes better. Okay, so this dropout is a very important and powerful technique. Okay, to be honest, okay, we talk about so many different techniques in this chapter, right? So, well, yeah, I mean, some techniques are now common sense. Okay, for example, activation function or initialization strategy. Okay, those are common techniques. Everybody uses it. Okay, without saying. But there are some other techniques. Okay, that we always use it. We always use them. Okay, for example, batch normalization. This is a technique that everybody uses, especially in CNN. Another one I would tell you is this dropout. Okay, dropout is used, okay, very, very often. Okay. So, of course, if you know a little bit about machine learning, okay, if you have taken machine learning classes, then there's a different way to explain why dropout works. Okay, think about this. Okay, assuming you have n neurons, okay, except the neurons in the output layer. Assuming you have n neurons, okay, in total, in your network, okay, and because every neuron gets to throw a dice to decide to participate in the training, okay, for every iteration, right? So it should be rare. It should be rare for 2 iterations to have the same neurons to participate, right? Because each neuron has, either participate or not participate in this training, right? So there are totally 2 to the power of n different, neural networks you could possibly have, okay, when you use dropout for every layer, right? Okay, I mean the simple, combinatorics tell you that, right? So think about this. If you have a couple of hundred, let's say 500 neurons, this is already very small neural networks. Okay, 2 to the power of 500. This is like a gigantic number, right? Okay, and think about this, the chance for 2 exact neural networks to get trained in 2 different iterations is very rare, because at most you probably only train the neural network for 1,000 times, 1,000 iterations, right? Or 10,000 iterations, compared to the 2 to the power of 500. It's nothing, right? It's nothing. So the chance for 2 exact the same neural network gets trained in 2 different iterations, if the dropout is applied, is rare. So pretty much, say if you train this neural network 1,000 times, then it pretty much means that you are training 1,000 different neural networks. Each time you train it for 1 iteration. Okay, you can explain the dropout kind of like that. if you are training the neural network for 1,000 times, it's kind of equivalent to you are training 1,000 different neural network, but each neural network is trained with one iteration only. Okay, so the result. What is the result? The result is the kind of combination of those 1,000 different neural networks. Okay, in machine learning area, this concept, okay, to combine like a lot of different models together for inference, this concept is called ensemble. Okay, ensemble. Okay, so if you know ensemble in machine learning, then you know ensemble is a very powerful approach. Okay, for example, one example I can tell you, okay, about ensemble is like you know decision tree, right? If you have taken machine learning, you must know decision tree. Okay, but you know decision tree normally doesn't perform very well, right? But random forest perform normally very well, right? Random forest is ensemble of a lot of decision trees. Okay, so same thing here. Okay, I mean if you consider each neural network that only gets trained for one iteration, the performance must be poor. Okay, but if you consider 1,000 of these combined to make a decision, then normally it will give you much better performance. Okay, so this is like another way to to explain why dropout improve the performance. Okay, so remember I told you like there's a small technical detail that we need to take care. Okay, especially after the training. Okay, here we go. Okay, basically, okay, if the p is 0.5, if the dropout rate is 0.5, okay, this kind of means like during the training, half of the neurons that give you the input, half of the neuron that provide the input to you, okay, assuming you are a neuron in a network, okay, approximately half of the neuron that provide input to you will take 1 day off, right? Okay, so after you finish training, remember I told you all neurons will remain active, right? So your input will be approximately twice as much, right? Your input will, but that will probably make the neural network work differently, right? Because the input number, the sum of the input will be different, right? So in order to make sure, okay, after training, you are going to get like approximately the same scale of the input. Then, okay, you have to sort of like after the training, when you do the inference, okay, then you need to downgrade. You need to downgrade your input by this dropout rate. Okay, or another way to say it is like okay, we multiply each input connection, okay, weight by what we call keep probability, 1 minus p, after training. So this is to ensure that, okay, when you are doing training, okay, remember half of the neurons are not working, right? On average. So you get this much input. After training, because all the neurons are active, so the input gets increased, right? So you should multiply the input by this keep probability in order to ensure you are getting approximately the same amount of input. Okay? Yeah. So alternatively, another way to do it is that you can divide each neuron's output by key probability during training. Okay, then after the training, you don't need to do anything. Okay, when you divide the neuron's output by key probability, obviously you increase the size, right? You increase the neural output during training. Okay, so after training, you just don't do anything, so it will remains about the same scale, right? Okay, so that's another approach. So either way, it works just fine. Okay, but you really don't need to write the code for that. Okay, in practice, okay, you can just apply dropout only to the neurons in the top 1 to 3 layers. Okay, normally. Okay, we usually apply dropout to the fully connected layers only. Okay, normally we only apply dropout to the fully connected layer, and as you will see later, okay, no matter we are talking about CNN or RNN, the last few layers are fully connected layers, and those layers are where we apply dropout. Okay, so it is fairly easy, very straightforward to apply dropout, okay, in your network. It's kind of just like batch normalization, okay? Remember in the batch normalization, you just, for every layer, you just add one sentence and that's it, right? One statement and that's it. Same thing, okay? For example, okay, here is the example, okay? This is the example for the fashion MNIST, and if you want to apply dropout to every layer, okay, you can see the flatten, okay, and then we apply dropout here for the flattened layer. So the dropout rate is 0.2, okay, and then the first hidden layer, dense layer, we have 300 neurons, okay, and we apply dropout with a dropout rate 0.2, and then we have second hidden layer, okay, and we apply dropout to this second hidden layer with dropout rate 0.2, and then we have the output layer. Remember, we don't apply dropout to the output layer, okay, so that's it. It's so simple. Then you have a model that comes with a dropout. Okay, very, very simple. And you may ask, okay, because dropout rate obviously is a hyperparameter, right? It's a hyperparameter. So you may ask, what value should we use? Should we use a large dropout rate or small one? Okay, well, sometimes it really depends on your model is overfitting or not. Okay, if the model is overfitting, what does that mean? It means you have too many parameters, right? You have too many parameters, and the data size is too small, right? Either way you explain that. So in that case, you should increase the dropout rate. Why? Because when you increase the dropout rate, you can imagine, when you increase the dropout rate, the people who come to work, okay, for company, the number of people who come to work for company every day gets reduced, right? Right? Because when the dropout rate increase, okay, the number of people who come to work every day, or the number of neurons who participate in the computation gets reduced, right? Okay, that means intuitively you will have lower number of parameters, right? More neurons, more parameters, obviously, right? Okay, so because you are overfitting, so obviously you should reduce the number of parameters. So an indirectly approach is to increase the dropout rate. Okay, but on the other hand, if your model underfits, then you should reduce the dropout rate. Okay, so it depends on the performance of your model. Okay, so many state-of-the-art architectures only use dropout after the last hidden layer. Okay, so you may want to try this if full dropout is too strong. Okay, you don't have to apply dropout to every layer. As I said, normally you only apply dropout to the last few layers. Okay, you could apply dropout to every layer like this, except the output layer, of course. But you don't have to. You don't have to. If you feel like you are using dropout too much, then obviously you can you don't have to do that. So dropout does tend to significantly slow down convergence. Why? Because every neuron has to generate a random number to decide to participate in this training iteration or not, right? So it takes time, right? It takes time. So the iteration, the time for each iteration, it will increase slightly. Okay, so obviously it will slow down the training. Okay, it will slow down the training, but okay, it usually result in a much better model. Okay, as long as you have you tune properly. I mean, when I say tune properly, I mean like you apply dropout at the right place with the right dropout rate. Okay, so I mean this better model, okay, will have a better performance. So it is generally well worth the extra time and effort. Okay, so dropout is an important technique. It's a simple to apply and usually give you a boost in the performance. Okay, so you should try it. Okay, sometimes. So since dropout is only active during training, okay, comparing the training loss and the validation loss may be misleading. Okay, so in particular, a model may be overfitting the training set and yet have a similar training and the validation losses. Okay, so this, okay, you have to remember, make sure to evaluate the training loss without dropout. Okay, in other words, okay, after training. Okay, otherwise the learning curve may mislead you. Okay, may mislead you. Okay, and also, okay, remember we already talked about CLU. Remember we talked about CLU, this special activation function that can do self-normalizing, right? Self-normalization, which is a very nice feature. Okay, so if you use CLU to build a self-normalizing network, okay, then you shouldn't use regular dropout, because regular dropout is going to hurt this self-normalization property. Okay, it will not maintain. You will not be able to maintain the self-normalization property. So there's another variant of dropout that you could use. When you use CLU to build a network, which is called alpha dropout. Okay, you can apply alpha dropout to be able to maintain the self-normalization property that you have when you use CLU to build a network. Okay, so keep in mind, for CLU-based network, use alpha dropout, not a regular one. Okay, regular dropout would break self-normalization. Okay. Oh, it really hurt my throat. Can someone, well, but if we close the window, it's going to be very hot, right? At least can you shut that window halfway? 至少关一半，好不好？ Yeah， 关一半这样子。I don't know what are you doing? Okay, well, okay. So there's another technique called Monte Carlo dropout. Okay, or abbreviated as MC dropout. Okay, do you guys know mathematically when we say something Monte Carlo something, what does that mean? Okay, what is the term Monte Carlo refer to? Monte Carlo is Monte Carlo. Okay, it's a name of a place. Okay, it's the name of the place. Okay, that place is famous for gambling. It's famous for gambling. I mean, today when we talk about gambling, which city is more popular? It's more famous. Las Vegas. Okay, Las Vegas. Yes, or Macau maybe. Right? If you are in Asia. Okay, but unfortunately, Las Vegas is it's a new city actually. Okay, when I say new city, I mean it's about like a little bit more than 100 years, I think. Okay, so but mathematics has been there for several hundred years, right? So in the old days, okay, a couple of hundred years ago, okay, which place has a more advanced technology? Not China, okay, unfortunately, okay. It's Europe, okay, Europe, especially French and Germany. That's why, okay, if you look at like World War I, World War II, okay, I mean, they both are, they both happened in Europe, right? Okay, because at that time, the Europe is the center of the world, okay, and most of the important findings happens in Europe, okay. Well, to be honest, at that time, like the paper, okay, technical papers, normally are written in Germany or in French, okay, not in English, okay. I mean, you see like English dominate like international like world. It happened only like in recent like maybe 50, 70 years only. Okay, that's especially after the World War III. Okay, so back to that old days. Okay, the most famous gambling city is Monte Carlo in French. Okay, so if you are describing a technique that involves random property, randomness. Okay, if you are describing a property that involves randomness, it's kind of related to gambling, right? So people will describe it as Monte Carlo something. Okay, so when you see Monte Carlo, okay, you have to understand first it refers to a gambling city in Europe. Second, okay, then if you try to translate it, it basically just means random. Okay, just means random. Okay, so what is Monte Carlo dropout then? Okay, first, okay, a paper, okay, in 2016, a paper by Yarin and Zubin, okay, they provide a few interesting findings. Okay, there are two most important findings. First, okay, this paper established the connection, okay, between dropout and you know, approximate Bayesian inference. Okay, you know, they actually provide a theoretical foundation between these two different approaches. I know like you guys probably do not know what is Bayesian inference. Okay, just in case if you don't know. Okay, I offered a class called Bayesian data analysis next semester. So if you are interested in Bayesian data analysis, okay, you are more than welcome to take my class. Okay, but well, it's another branch of you can call it statistical inference. Statistical inference. Okay, so first that paper established the connection between dropout and approximate Bayesian inference. Okay, so they provide the foundation between these two approaches. Okay, second, okay, that paper introduced a powerful technique called MC dropout. Okay, this MC dropout is very interesting. Okay, it boosts the performance of a trained dropout model. Okay, be very careful. This model is already trained. Normally, you cannot improve a trained model, right? If a model is trained, well, it's just there, right? You don't normally cannot improve it, right? But if a model is trained by dropout, okay, the MC dropout actually, you know, is able to improve the performance, okay, and also, okay, without the need to retrain the model, okay, you don't need to retrain the model, or you don't need to modify it at all, okay. So it's a very convenient approach, and providing a much better measure of the model's uncertainty, and it's also amazingly simple to implement. Okay, so what exactly is this? Let me show you an example. Okay, here, assume we use dropout to train this model to recognize to classify the facial MNIST. Okay. Assume we already have a trained dropout model here, okay? And then, okay, these two statements, can you guys understand what we are doing here? For sample in range 100, so we are going to do this 100 times, okay? This 100, so basically we are, you know, we are trying to, you know, stack I mean, using the test set, we are using a test set to do inference. So for every inference, okay, we get the probability for each class, okay, and then we stack up the whole thing, okay, and you know, in range 100, that means we pretty much do this for every instances in the training set, okay, for 100 times. But you may say, oh, if we do this, I mean for one instance for 100 times, we are going to get the same thing for 100 times, right? But be careful. We set the training to be true, right? When you set the training to be true, okay, remember this model is a dropout model, right? So the dropout property will be activated. So every time this model tries to do the inference, okay, some neurons will be dropped, right? Some neurons will be dropped. Okay, every time you use this neuron to do the inference. So even if you use this trained model to do inference for the same instance for 100 times, you are going to get the 100 different results. Okay? Because every time the model have some different neurons to be dropped. Okay? and then we do average. Okay, for x equal to 0 means like I will explain this shortly. Okay. So here we just make 100 prediction over the test set. So for every instance in the test set, we do 100 predictions, setting training to be true, okay, to ensure that the dropout layer is active. So that, I mean, for this 100 prediction, okay, you are pretty much, make sure like a certain neurons get dropped, okay. So, I mean, when you do the inference. So you are going to stack the predictions result together, okay? I mean, one after another, okay? And then, okay, since dropout is active, all the predictions will be different, okay? And that, recall that predict returns a matrix with 1 row per instance and 1 column per class. So, because we have 10,000 instances in the test set, okay, in the fashion MNIST, we have 10,000 instances in the test set, okay. So, okay, and 10 classes. So this is a matrix of shape 10,010, okay. So this is this shape represent the test set, okay, the shape of the test set. But now we are doing this for 100 times, right? For every instance, we are doing do this inference for 100 times. So at the end, okay, we stack 100 such matrix. So this Y probus is going to have a shape 100 10,010, okay, and then we are doing the average over the first dimension. Okay, x is equal to 0. Okay, this x is equal to 0 means, okay, because this is dimension 0, dimension 1, dimension 2. So we are doing the average over this dimension. So we basically get the average for the, for these 100 inferences. Okay, and that's it. Okay, so we are going to get a shape 10,010. Okay, and that's it. So basically, like it just means like for every instance in the training set, we try to do the inference for 100 times, but we turn on the dropout property, dropout layer, to make sure these 100 inference are done slightly differently. Okay, so we get that 100 different results, right? And then we do the average. Okay, we get average done. Okay, so okay, if you only inference one instance one time, this is the result. Okay, so basically you are going to output like a probability for each class, and you can see that. Okay, well, for this for the first instance in the test set, okay, and we are trying to use this predict, okay, use the model without turning on the dropout. Here we do not turn on the dropout. So you can see that, okay, it tells you 99% of the case, this instance is the last class, right? 99%. Okay, it is very, very certain this instance belongs to the last class, and it has like a 1% chance this belong to the 10, 9, 8, the eighth class. Okay, so what is this? This instance, by the way, this instance is an ankle boot. It's an ankle boot. Okay, and then so it knows that this image belongs to class 9 with very certain, very positive probability. Okay, but it also say it could be class 7, right? Class 7. which is like you know, the eighth class. Okay, the eighth class. What is eighth class? Or class 7? Class 7 is a sneaker. So you can see that, well, ankle boots, because if I mean, for ankle boots, it's kind of similar to sneaker, right? In the sense that they are both, you know, shoes, right? They are both shoes, right? But this model is very certain it's a ankle boot. Okay, it's ankle boot. But once you turn on the dropout and do the inference by using the same model, see, this is like the probability that it gets inference for every class. You can see that, okay, now, okay, of course we can still see the last class has the highest probability. The ankle boot still has the highest probability, but it's not so certain anymore, right? Okay, it's much lower. Originally it's 99%. Now it's 68%, 64%, 97%. It's much lower than 99%. And now, okay, it says, oh, it could be the you know, well, class 0, class 1, class 2, class 3, 4, 5. It could be class 5. It could be class 7, okay, with certain probabilities. Okay, so what is class 5? Class 5 is sandal. Class 7, as I said, is sneaker. So they are, you know, no matter it's a sandal, it's a sneaker, or ankle boots, they are all shoes, right? They are all shoes. So it tells you that, okay, now, okay, you know, we are able to use the model to tell you a different story. That, okay, some other classes may also be possible. So it tells you a much more, you know, information than the original one. Okay, that does not turn on the dropout. Okay. So if you try to do the average, remember we try to do the average for those 100 inferences. So the result is like this. You can see, okay, for class 5 it's 22%. For class 7 it's 16%. For class 9 it's 62%. Of course, the highest probability is still ankle boots. But you can see it could be class 5 and the class 7 with a non-neglectable probability, right? With a non-neglectable probability. And this is important. Okay, why is this important?